Let's talk about magnets. So we talked a lot about magnets last week, but we didn't really talk about where magnets come from, except to say, sometimes quantum mechanics happens and magnets is the result. Which is true, but it's not like the whole story. So there is so we talked also about how magnetic fields can produce a force on charged particles. Right? This is the Lorentz force. This is also not the whole story. Because it turns out that this equation actually works the other way too. That magnetic fields produce a force on moving charged particles, but moving charged particles also create a magnetic field. And today we're going to talk about that reverse direction. So we are not going to go super in depth into the mechanics of it at this class, because to even make a start of it, you need 3 semesters of calculus. So the law that governs this sort of behavior for steady currents and steady magnetic fields, you have to do what's called a contour integral. So the integral of a B field around a loop is equal to the current flowing through that loop. We don't have the tools to deal with that. Straight up. So instead, we're going to focus on one really important special case. So if the current that we are talking about is carried along a long straight wire, right? So current is going that way. And this wire is real long. And when a physicist says real long, that's actually code for infinity long. If this is the situation, then the magnetic field produced by that long wire is equal to the magnetic permeability times the current in that wire divided by 2 pi times the distance from the wire. So at a distance, say up here, if you were that far from the wire, then this is your R here. Using the right-hand rule, right, to determine the direction of the B field, point your thumb in the direction of the current, and your fingers will curl in the direction of the B field. So the B field created by this long wire is actually going to come out of the page on this side, and it's going to go into the page on this side. So the B fields curl around the wire in a circular loop. So if we were looking maybe end on, so here's the end of the wire, the direction of the B field is that way. That's right, Daniel. No quiz today. Jessica, what symbol is that next to B? In this thing, that is the symbol for a contour integral, which you would encounter near the end of your 3rd semester of calculus. So we definitely are not going to make direct use of this at all. And in fact, the only special case that's even mentioned in your book is the B field for a long current carrying wire. So do you remember in Gen Phys 1 where we had we did moment of inertia calculations, right? And the moment of inertia depended on the shape of the object that you were considering. So if you had like a circle and you were thinking, well, what is the moment of inertia of this disk about its center? And at this level, we didn't do any calculations of moment of inertia. We just looked them up, right? 1/2 mr squared. That's the moment of inertia of this disk. You all remember that from last semester, right?
Yeah, of course.
Yep, 100%. Okay. Um, so there were like a few of them in your book, like for a disk, for a point, for a rod, for a sphere, maybe. Um, and all of these came from a pretty satisfying integral that you could do after one semester of calculus. But because we're trying to keep calculus out of this level of math, they just gave you the results. This idea that about the B field of a current through a long wire is along the same route. Like we're not going to do the calculus, but here's the result. This is what you would get if you did do the integral. And if you, if you were to look up other shapes of charge, you'd get other other expressions. But the wire ends up being enough for our purposes, because most of the stuff that we are concerned with is actually made out of wire. So for a straight piece of wire, we've got the B field wrapping around it. But what if we take that same wire and we make a loop? And current is going, say, clockwise around the loop. Well, now we've got this situation where this B field is coming out of the page on the outside of the loop, and it's going into the page on the inside of the loop. And if you take a bunch of these loops and you coil them together, then you have a solenoid. And the B field is going to go, that it creates, is going to go through the solenoid and then kind of do one of these. And the current is going to wrap around the purple bits. So if you've ever worked on your car and maybe the starter went out and the mechanic said that you needed a new solenoid, this is exactly what he was talking about. It's just a coil of wire that when you run a current through it, it creates a magnetic field that's pretty uniform right down the center of the coil, and that magnetic field it creates is what jump starts the engine to your car when you turn it on. All right. Questions or comments?
I have a question really quick.
Yes.
Before you switched to this and you had the long line, the wire, and you had the dots, or the circles on the top and the X's on the bottom.
Mm-hmm.
Yeah, so you were saying that The something rotates around the wire. Was it the current rotates or is it the B field?
The B field. So the current is going straight down the wire, but the B field it makes is like swirly, right? It goes
Okay,
clockwise around or counterclockwise around here.
perfect. Yeah, it didn't make sense. I thought you said current and I was then confused
Oh,
how it would run down the wire. So thank you.
oh, yeah. I may have said current. I haven't had enough coffee. All right, so this discussion here, that is 22.9. 22.10 leads us to a discussion of a problem, actually. So last week, we discussed that a B field on a wire carrying a current causes a force on that piece of wire. Right? So if we had a wire with current and we had a B field, then we would have a right. Our force is equal to I L B sine theta, where I is the current flowing through the wire, L is the length of wire that we're considering, B is the strength of the B field. What's the direction of this force?
To the left?
So,
No, wait, sorry, wrong. Yeah, into the page.
Isn't it rotating?
Or no?
yeah, Jessica's got it. So, right hand rule, you point your thumb in the direction of current, your fingers in the direction of the B field, your palm is pointing in the direction of the force. So this force, the way we've drawn current in B field here, that would be into the page. So that's all well and good. But what if we have two wires? Right, so we have one wire next to another wire, which, we might have if we've got a circuit, right? And we're carrying current through the circuit to do various things, and we just happen to have two wires that stray near each other. So in this case, we're going to have a B field. Let's see, we'll call this 1 and 2. There will be a B field due to wire 1, which is equal to mu naught I over 2 pi r, where r is like the distance from wire 1. So let's actually say these two wires are a distance r apart. And the direction here, right, by the right-hand rule, the B field is going to be coming out on this side of wire 1. It's going to be going into the page on this side of wire 1. So the force on wire 2, right, is going to be I2 LB1, right? And what direction is the force on wire 2 because due to this B field? Well, so current's going up, so point your thumb in the direction of the current. The B field is going into the page, so and palm will be in the direction of the force. So that force is actually going to the left. So all right, let's do the same thing, but we'll start with wire 2. So there'll be a B field created by wire 2. Same expression. And wire 2, right? Right-hand rule, current goes up, curl your fingers around. The B field due to wire 2 will be going out of the page on the left side of wire 2. It'll be going into the page on the other side of wire 2. And the force then on wire 1 will be I1LB2. And again, let's break out our right hands. So current going up, B field from wire 2, the blue B field is coming out of the page, so our palm's pointing to the right. Now let's plug in what we mean by B1 and B2 in these forces. So the force, right, B1 here is mu naught I1 over 2 pi r. There's a, and then there's also an I2 there. So this will be the force between two current carrying wires. So if you have two wires parallel to each other and they're close enough to feel these B fields, if the currents are going in the same direction, these wires are going to be attracted to each other because of the B field that they create. If they're going in opposite directions, they will be repulsed from each other due to the B field they create. So this is more of a cautionary tale than a useful phenomenon, since usually this just means we have to be really careful of the amount of current that we run through very small circuits, because we can physically rip wires apart by running too much current through them and creating too much B field. Okay. Questions or comments?
Question.
Yeah.
In order to change the direction of the B field, we just change the direction of the current.
You got it.
Okay, thank you.
So if I1, for example, if I1 had been pointing down, right, then the right-hand rule would suggest that the B field it creates was circulating in the opposite direction.
So in like a real world application, that wire would be running, it'd be like positive to negative in one direction and then positive to negative in the other direction, like they're opposing forces.
It's something you definitely have to keep in mind.
Okay.
Right. Especially like if you think about it, the chips that your computer processors are printed on, the wires are only 14 nanometers apart in a modern computer. That's really close. so the little tiny wires on the processing chip, they actually feel the B field of nearby wires quite strongly.
And that doesn't mess with them at all?
It absolutely messes with them. That's the primary reason, not the primary reason, but it's a big reason why your processor wears out. Right? So like processing chips, they don't last forever. And this is one of the reasons why. So the biggest reason is heat, right? So the power that goes through a resistor, like a little piece of wire, is equal to voltage times current, and that makes heat. That power gets dissipated as heat, and that heat melts the copper wire that is in the circuit. And then the second big thing is that if you are not careful with the B fields that it's created, that you can pull wires out of their place. But actually, that effect is smaller than the next thing that we are going to consider. So thank you for setting up that segue for me. Constant currents produce a constant B field. But changing currents and also produce changing B fields, and changing B fields produce not just changing currents, but they can produce voltage out of nowhere. That's what we call electromagnetic induction. Before we get super into that, I need to talk to you about a concept called flux. So we've been talking about fields for a while now. Electric fields, magnetic fields. All right. So flux is a way of measuring how much field is going through, say, a surface. So if we've got B fields going in, we've got some cross-sectional area of this loop, let's say. Also, let's pretend that I could write in a legible fashion. If the B field is going straight into the loop, then great. That makes it easy. The amount of flux, and we usually use this Greek letter phi for flux, is just equal to B times A. That's how much flux goes through this loop. But what if the B field is not so nicely oriented, right? So if we have a B field coming in like this, now we get to break out our vector skills from Gen Physics 1. And a B field that's oriented like this, we can actually split it up into two parts. We can split it up into one part that is going parallel to the surface of this loop, and one that's going perpendicular to the surface of the loop. But for historical reasons, we don't usually think we don't want to think about parallel or perpendicular to the plane of the loop. Instead, we think about the normal vector of the loop. If you had taken Gen Physics with me, you would know that normal is just an old-fashioned fancy word for perpendicular. So if you have a surface, say the floor, the normal force that the floor exerts on you is going to be straight up. Very similarly, the normal vector of a surface is perpendicular to that surface, and it's a convenient way of determining the orientation. Like, what way is this surface pointed? So like the normal vector for this loop that I've drawn here, it would be, we would draw the normal vector starting in the center of this thing and then perpendicular to the surface to the left. So when we have this B field coming in, we break it up into two components using the vector skills that we worked on so hard in Gen Physics 1. But the components aren't X and Y, they are instead normal and parallel. Let me draw in here. So pretend this is the normal vector of our surface, and this is the B field that's coming in. By convention, the angle that we're concerned with here is this angle here, between the theta, between the normal vector of the surface and the B field. So the part that is in the same direction as the normal, so the B field that's normal to the surface here, that's the part that's going to actually go through the surface. And the part that's parallel, it's not going to go through the surface, it's going to just skate along it, but it won't be going through it. Have I completely lost anyone with this this idea of breaking down a vector into parallel and perpendicular components?
Didn't you just say that normal was another way of saying parallel?
Normal is a way of saying perpendicular.
Oh, perpendicular.
Yeah. Okay. So we add a cosine theta to our idea of flux. And then lastly, because we're almost never talking about just one loop at a time, right? We're usually talking about stacked loops, solenoids or coils or something like that. We toss in this n. So this is number of loops magnetic field area of the loop and the normal component only. Right. So far, so good? Questions, comments? All right. So far, this is just a definition. This is what we mean when we say flux. How much field is going through a loop? Just a mathematical definition so far. Here's the physics. If you change the magnetic flux through a loop, you create a voltage. This is the huge payoff. This is what makes basically all of modern society possible. Right? You change that flux, you get a voltage. This is how all of our electricity gets made, except for solar. Solar's the odd one out, but everything else.
Is the T time or turn?
Time. So the amount of voltage that you get is equal to the rate at which you are changing the magnetic flux. And this is called Faraday's law. Let's take a closer look. So, to recap, the things that go into the flux, right? The number of loops, the strength of the B field, the size of the loop, the orientation of the loop. If you change any one of those things, you get electricity, right? You get voltage. And once you have voltage, if that voltage is on a metallic wire, apply a voltage to a wire, you get a current, and bam, electricity. In practice, it is hard to change the number of coils, or the number of loops in a coil. It is hard to change the area of the coil. And if we're using permanent magnets, right? So if we're using like neodymium magnets or iron ferromagnets, we don't get a choice about how strong the B field is. It's just as strong as it is. Right? Our magnet is what it is. And so, that leaves us with just the ability to change the orientation. So, essentially all methods of electrical generation operate under this principle. Again, except for solar. You have a coil of wire, many, many loops probably. You have a magnet inside that loop. Right? And then you spin the magnet. Right, into and out of the page in this case. You find some way to spin that magnet, you are going to create electricity in that coil of wire. The only differences between the different kinds of power generation we have is how are we spinning that magnet. So if we have hydropower, like out at Hoover Dam, we get falling water that we put a turbine in the path of that falling water. Like you imagine an old-fashioned water wheel, basically. That gives you the essentials of it. Falling water, we put a turbine in its path. That water spins the turbine. And the spinning turbine spins a magnet. If we have a fossil fuel plant, we make fire. We use that fire to boil water. When the water boils, steam rises. We put a turbine in the path of that steam. That turbine spins a magnet. If we have nuclear power, we split a radioactive atom. Neutrons fly everywhere. Those neutrons boil water. That water turns into steam.
Beginning to see a pattern.
Yeah, and we stick a turbine in its path. Questions or comments? Solar works through the magic of quantum mechanics.
What about air turbines?
Air turbines, or wind turbines. Wind is moving. You stick a turbine in its path. You spin a magnet. Tidal energy. Tide goes in, tide goes out. You stick a turbine in its path, it spins it one direction when the tide goes in, spins it the other direction when the tide goes out. Either way, you spin a magnet. So yeah, so except for hydro, we are just looking for interesting ways to boil water. In fact, even the early solar energy, before we had photovoltaic panels, we put mirrors out in the desert, focused it on a tank of water, made steam. All right. So that's Faraday's law. The next thing to think about is Lenz's law. So Faraday's law says you make voltage through the use of changing electric fields. Lenz's law tells you which direction that voltage is going to point. Let's make a graph. If we're spinning magnets or turbines, by the way, so we are sketching out a cosine function as we spin, right? So the voltage, and your book, by the way, your book uses EMF instead of voltage. I don't like that. EMF stands for electromotive force, but this isn't a force. It's a voltage. Let's just call it what it is. So the only thing that we're changing with our normal power generation is we're changing this cosine theta, right? And I think most of you have had one semester of calculus. So you know that the rate of change of a cosine function is actually a sine function. But if you didn't know that already, just take my word for it. So at this point in the graph, right, we have a rising change in flux, right? Because our function is positive. Actually, we'll draw let's see if I can draw a cosine function here too. So close. All right. I can't do both at once. I just can't. All right, so here's our cosine. If we're at, say, this point in the cosine, our value of cosine theta is decreasing. Right? So our flux is going down. Lenz's law says that the direction of the induced voltage will tend to counteract the changing magnetic field that caused the voltage in the first place. So if here's our solenoid, our coil of wire, and if our flux is decreasing, that's the same as saying that our change in flux is pointed that way. Which means that that tells us actually what direction our current is going to be pointing. Because if we had a couple of screens ago, if we have a current going through one of these coils, we're going to make a B field, right? So if our change in flux is to the left, and that's creating a current, the current that is created is going to make a magnetic field that points to the right. What direction does the current need to be to make a B field that goes to the right? Well, to do that, we need, if we use the right-hand rule, thumb in the direction of the B field, fingers curling around top. So we need the current to be going, so the current will be coming out of the page up here and into the page down here. So that is the direction that the current is going to be swirling around the solenoid. I know, Lenz's law is a mouthful, right? Changing magnetic flux causes a current. Well, causes a voltage. Voltage, due to Ohm's law, causes a current. That current causes a B field. And Lenz's law says the B field that you ultimately create is going to point in the opposite direction of the changing flux that started it off. I hope that came out better than it sounded when I was saying it. Comments or questions there? Overall direction of I depends on the way the wire is coiled. Is there more than one way to coil a wire? I guess so. Yeah, the direction of the winding. Yeah, the counterclockwise or clockwise winding. Yeah, no, you're right. That is a good observation. All right, so we just covered sections 23.1, 23.2, and 23.4. Or sorry, 23.5. 23.3 considers the case where instead of changing the orientation of the magnetic field, we actually are changing the area of the loop that the B field goes through. So if you look at 23.3, I'm not going to go over it explicitly because it follows the same rules, right? So a changing flux creates a voltage, except here it's actually the changing area of the coil, of the square coil, that is causing the change in flux, and B field orientation are constant. In 23.4, again, it's the same idea. We're changing the flux, except instead of changing the orientation of the B field, like you do in a generator, you're actually moving the whole loop. Like you're swinging this loop through an area of magnetic fields. And so you have not just a changing amount of flux due to the changing orientation, you also have moving charged particles because you're swinging the entire loop. All right. So those two sections, 23.3 and 23.4, I won't be covering directly in lecture. They are still interesting, and you should definitely work some problems from them, but their scope is relatively limited. Any questions? Anthony, that's a good question. So how do you know the direction of the change in flux? So this is this is like the question of velocity versus acceleration in Gen Physics 1. So acceleration is right. The direction of the acceleration is like the direction of the change in velocity. So if you are slowing down, then the direction of your acceleration is opposite the direction of your actual velocity. Whereas if you're speeding up, the direction of your acceleration is in the same direction as your actual velocity. And that's the same what we've got here. If the change in flux, right? If your flux is increasing, then the change in flux is parallel to the B field. But if your flux is decreasing, then your change in flux is opposite the B field. Did that answer your question? Okay. Okay. I would like to talk briefly about transformers, which is section 23.7. So in general, a transformer is any electrical device that changes the voltage of the electricity running through it. And the way it's generally done is through having two coils of wire that are not connected to one another. So you have an input coil, and you have an output coil. And so, they're not touching. So how do they, if they're not touching, how does electricity get from one side to the other? Magic. I mean, only if you consider magnets to be magical. Yeah, we're actually transferring that energy over in, via magnetic fields. So, and actually the reason why these devices even work is because we operate off of alternating current. So, right, so Faraday's law says the voltage that you create is the change in the flux versus the change in time in all of the generators that we use, right? Whether they're nuclear or fuel or hydro or whatever. We're spinning some magnets. And in the United States, we spin them at a rate of 60 times per second. So the current, so the voltage that we create is also, it falls and peaks at 60 times per second. That's why the frequency of electricity in the US is 60 hertz. This was not always the case, right? In the turn of the century, like gold rush times, there was a huge chunk of Southern California that includes what is now LA. All of their generators ran on 50 hertz. So they actually could not get electricity from the larger electrical grid. They had to generate all of it at home. So the voltage here, the voltage you create is, right, so NAB, right? B is the strength of the magnets you're using, A is the area of the coil, N is the number of turns in the coil. Those are all fixed parameters of your generator. Once you build it, you can't change them. But you can change this orientation. And the rate of change of a cosine is actually a sine. And if you remember Gen Physics 1, right? An angle is an angular speed times a time. And in the United States, that's 60 hertz. So we actually, this is 2 pi times 60 hertz times time. So the voltage that we get out of our wall socket varies as a function of time, but it varies quickly, very quickly. By the way, does anyone know, or does anyone want to guess, why we chose 60 hertz as the frequency for our electricity rather than something like 30 hertz? There is actually a very good reason for it. And it's not just because 60 is a nicer number than 30. Anyone here play video games? What's better? Playing a game at 30 frames per second or playing a game at 60 frames per second? And can you tell the difference? Yeah, 60 FPS is way better than 30 FPS. So if you're, so the frequency of the electricity coming into your house is also the frequency with which the light bulbs in your house flicker. If the frequency of your electricity is 30 hertz, your light bulbs are going to flicker 30 times a second, and that is visible to the human eye. But if they're flickering 60 times a second, now that's invisible. So we chose 60 hertz so that the flickering light bulbs in our house would not give us migraines. Okay, historical bit aside. What if they increase the number? You get less and less benefit, especially with modern light bulbs. Modern light bulbs have a bunch of capacitors stuck in them too. So actually, in a modern LED, you wouldn't even notice the flicker at 30 refresh cycle. So you get less and less benefit out of going to a higher number, but it is more expensive. In fact, Europe does not use 60 frequency electricity. They use 50 frequency electricity because it's cheaper to produce, and mostly you can't tell the difference. There are no countries that use higher than 60. Japan has the honor of being the only country in the world that produces both 50 and 60 hertz electricity. So whether you are north or south of Tokyo determines what kind of electricity you'll get when you plug stuff into your outlet. Why would they do that? That is an excellent question. I think they started off doing that before there were national electric grids, and now they just can't be arsed to change it. Okay. So all that aside, here's our voltage. That means the current in the purple bit is also, a sinusoid. So I'm just going to plop a beta out front for, or actually, you know what? No, don't plop a beta out front. Let's say this is like let's look at the transformer that's it's probably outside your house, right? So the electricity that comes through the power lines is something like 10,000 volts. And we want to step that down to something reasonable. Right? So coming in, 10,000 volts of electricity. Going out, 360 volts of electricity. And that actually gets split off even more so that you can get 120 volt electricity in your house. Okay. So I'm not like a huge fan of the way your book covers this topic. I think they give too little information. So I'm going to do a little bit more information here. So the current that we get through this primary here is say it's the sum maximum current times sine omega t. Right, so it's a varying current. Because this current is varying, right? The B field that the current produces is also varying. Right? So remember, the B field for a current for just a single piece of wire is equal to mu naught I, right, over 2R. But if this I is now, boop, a function of time, your B field also a function of time. So in the purple coil, you create a B field. And the orange, the secondary, is close enough so that the B field from the purple coil actually passes through the orange coil. So on the orange side, so on the purple side, we're creating a B field that changes in time because the current that we're using changes in time. On the orange side, we are inducing a voltage by changing the strength of the B field. Everyone with me?
Sure, why not?
we're not going to do any in-depth calculations about rates of change of B fields or anything like that. We do want a general statement, though. In practice, when we are making these transformers, they are all made out of steel. And that's because, as we noted with the wires, if you have strong B fields, high currents, you have lots of magnetic force on the current carrying conductors. So we make these transformers out of steel so that they can withstand all of the forces. The voltages that you put in and the voltages that you get out. So okay, let me back up. So the only difference between these two coils, right? Same size, same material. The only thing that's going to be different between them is the number of turns that we are wrapping the steel wire for our coil. Right. All of this above the pink line is just background, because the payoff is that the product of voltage and turns is the same. Sorry, wow. Not the product, the quotient. I am a little off my game today. So here, P is what we call the primary coil. So that's the one that we're putting the 10,000 volts into. S is for a secondary coil. It's the one that we're only getting 360 volts out of. So this is the relationship for coils that are identical except for turns. Okay. The entire point of this chapter, by the way, is not to do detailed calculations. We don't have the time to cover in that depth. What I'm looking for is plausibility, right? So we have one big physical idea, and that's that changing magnetic flux causes electricity. And that that principle, right? That's what I'm actually wanting you to remember. So like this, super important. Everything else, we're not like I said, we're not doing detailed proofs or calculations in this class, but we are using this as like a plausibility explanation for why all of this stuff in our everyday lives does work, and maybe a little bit of explanation for how well it works, why it works, right? So the idea is not to make you an electrical engineer in the space of a month and a half, but to maybe demystify it a little bit. Like there's nothing particularly magical about modern electronics. They are just collections of wires, coils, and capacitors that manipulate electric and magnetic fields. Okay. At this point, I would like to take a break. And when we come back, we will cover 23, 9, 10, 11, 12. That'll be the more detailed half of this chapter, where we actually can do some calculations about how relatively simple circuits behave. So my clock says 12:42 right now. Let's come back at 5 to 1, so 12:55. We'll take a 13-minute break. And I will see you all then.